One way of seeing the effects of induced charge is with this device right here, which is called an electrophorus. It's a piece of metal conductor on an insulating stick, and this is an insulating surface panel right here. What I'm going to do is I'm going to charge up this panel. And I don't really know what charge it is, but I know when I rub an amber rod with fur, it gets a negative charge. So I'm going to assume that this panel here is getting a negative charge, and that the fur is going to be positive. So got it nice and charged up. I'm going to touch this all over so I can ground it, and I know it doesn't have a charge. And I'm going to put it on the charged surface. I'm going to pick it up and I'm going to go over to the electroscope and check. And as you can see, there's no charge on it at all. So here's a look at that experimental setup. The white plate is supposed to be the charged plate, which I've said got a negative charge. I said the fur got a positive charge. And again, I don't really know that. But there's my electrophorus sitting on it. And you can see that a charge separation's been induced. The electrons in the metallic electrophorus, they fled as far as they could through that metallic bonding away from the charged plate. So there's going to be more negative charges on the top than there are on the bottom. Now, I picked it up and I moved it away from the plate. There's now no reason for those charges to remain separate. There's nothing forcing the negatives away from the positives. So they're all going to go back. And we're going to be left with an uncharged plate. So that's why when I took the electrophorus off, it didn't appear to have a charge on it. Once the negatively charged plate was removed, there was nothing to induce the charge separation. Because the plate was an insulator, it didn't transfer any of its charge to the metal electrophorus. I'm going to do it again, but I'm going to do something a little different. I'm going to touch the piece of metal. Did you hear that spark? The effect now is pretty different. This had a high charge on it after I did that. So let's attempt to explain this. So something very different happened when I touched the electrophorus. I think you guys could hear the spark. And what was actually going on there was I provided a bridge for the negative charges to get even farther away than they were originally. We have the charge separation because the negatives are moving as far away as they can get from the negative plate. But once I touch it, I give them another pathway. They can go up into my hand. So once that happens, there's actually less negative charges left in the electrophorus because some of them left and went into me. Now, it's not going to be the same situation when we remove the negative plate because I'm no longer touching it. And although those electrons that had gone into me could come back, since I'm not touching it anymore, it's like that route has been closed off. So we're left with an unbalanced charge. So these guys might recombine, but there's still some guys left over who don't have a matching charge. So the plate now has a positive charge. Here's another nice demonstration of induced charges. The setup I've got here is the Van de Graaff, which will get a strong positive charge. And I've got these two other spheres, which are currently touching each other. I'm going to run the Van de Graaff. We'll let it develop a nice big charge, and then we'll turn it off. And then we'll discharge the Van de Graaff, which is not touching the two spheres. Did that have an effect? Let's check this sphere on the left. Let's see if it has a charge. Does not appear to. I'm going to make one other adjustment in the routine. They're still touching each other. I'm going to repeat the experiment. But before I discharge the Van de Graaff, I'm going to separate the two. Let it run and charge up. Pull them apart. Off. Discharge. Now let's check the sphere on the left. As you can see, it's got a pretty strong charge. So what's going on? Well, when the two were touching each other, electrons could flow freely between them. And since the Van de Graaff dome was positively charged, electrons from both spheres flowed together into this one on the right. So there was a negative charge on the two spheres on the side closest to the Van de Graaff. So this is what that looked like. We've got our two spheres equally distributed, positive and negative charge. We bring in the positive charge, and we have all sorts of negative charge rushing to get closer to it. That's called an induced charge, and it leaves the other side more positive than it should be because the electrons left here and moved to here. Now, since they were connected, when I turned the Van de Graaff off and discharged it, all the electrons just went back where they ordinarily would. But the second time, when I pulled them apart, that couldn't happen. In that case, we still had our charge separation, but once we separated them, the positive charge was left on this one, the negative charge was left on this one, and there was no way for them to recombine. While the positive charge is there, they wouldn't try to, but once you take it away, you still have positive trapped here and negative trapped here. In this way, we've induced charges onto the two spheres. I have to give credit to Paul Hewitt for this type of drawing. It's in his conceptual physics book, and I think it's really the best way to visualize this. I've got one more example of induced charge that I would like to show you. Check this out. So what's going on is that one of those two soda cans is wired to the Van de Graaff generator, which gives it a large positive charge. The other soda can is strictly neutral. It's wired to the water pipe and then into the ground and into the earth. So this one has lots of electrons to either give or take. The pop tab's neutral too, but obviously its electrons are attracted by the positive can, so they get a little bit closer to it. They all kind of crowd, or a lot of them kind of crowd on the left side here, and that leaves the right side slightly positive. So the attraction between these negatives and these positives is more than the repulsion between these positives and these positives. And the tab just slowly drifts over until pow, it hits it. Now there's an electrical connection, and some of the negatives from the pop tab can go into the positive can and out into the Van de Graaff. That means that there's now a strong repulsive force on the pop tab because they're both positive. So it goes shooting across, and clink, it hits the other can. It gets the extra electrons it needs to become neutral again, and then it falls back, and the process repeats itself. So this is called Franklin's bells. Allegedly it was invented by Ben Franklin to detect lightning, but it's a pretty cool demo. Let's watch it one more time. And again, I want you to watch the attraction at first of the neutral tab until it first hits this one, and then it springs off it with such force it'll start ringing for a long time. Once the Van de Graaff's turned off, it actually keeps going until a lot of the charge left on the can gets carried off to the ground.